Hello everyone, my name is Anelisa Achilles and I will present the work A Comprehensive Energetic, Exergetic and Heat Transfer Analysis of a Solar Organic Rankine System that was developed with José Vicente D'Angelo at University of Campinas. One of the available options for power generation by employing solar energy is converting its energy into heat and electrical energy. This technology is named as concentrating solar power. It is mainly composed by a solar field, where the solar radiation is collected and concentrated, and a power block, in which electricity is generated. Among the feasible technologies to concentrate solar radiation in the solar field, parabolic flow collector, named PTC, is the most developed with better cost-effective performance. Considering the power block, organic Rankine cycle, ORC, has proven to be an effective thermodynamic power system to apply solar thermal energy, because it can bring about several benefits, like effectiveness in harnessing solar energy in low-medium temperatures, among others. The evaluation of the thermodynamic performance of a solar power plant in terms of energy, first law, and exergy, second law, may result in the identification of a proper effective configuration, giving us a better understanding to determine the quality, availability, and utilization of energy resources. Over the years, solar organic Rankine cycles have extensively been reported in the literatures in terms of thermodynamic analysis, as can be verified in the studies like Techanch et al., Haegan et al., and Yang et al. Although there is a field of study that covers this research area, it was observed that there is still a lack regarding research that analyze this subject in detail by considering both thermodynamic and heat transfer performances. Thus, the objective of this paper is to develop a detailed thermodynamic and heat transfer investigation of a solar organic Rankine cycle, by taking into account the energetic and exergetic efficiency for each component of the system, the exergy losses and destruction at all stages of the process, and carrying out a heat transfer analysis about heat losses, temperatures, and pressure drop of the solar field. In addition, it was made an assessment of the system performance under different solar radiation. The system under investigation consists of a 200 kilowatt solar plant as presented in the figure below. The mathematical model was developed in engineering equation solver. The solar field includes PTC collectors and terminal 66 as heat transfer fluid. The designed direct normal radiation, DNI, considered in this study was 717.2 watts per square meters, which was based on the meteorological data from Bom Jesus da Lapa in Brazil. The organic fluid chosen to drive the power block was cyclohexane, since it is classified as a dry fluid, so that it does not require superheating. Also, it has presented great thermodynamic performance in several studies. The heat collection element is composed by two concentric tubes, a receiver, through which the terminal flows, surrounded by a glass cover. Among them, there is an evacuating region called a nucleus, in order to reduce heat losses. Thus, the collector model uses an energy balance between the fluid flowing through the receiver and the atmosphere. The heat transfer in the receiver, as demonstrated in the figure, is given by solar energy reflected by the mirrors, in most absorbed by the receiver, and an insignificant quantity is collected by the glass cover. Part of the energy absorbed into receiver outer surface is transferred to its inner surface by conduction and then to the terminal by forced convection to increase its energy content until it achieves the required temperature. The energy that remains is transferred back to the glass-covered inner surface by radiation and natural convection, and passes through the glass by conduction. Then it is lost to the environment by convection and to sky by radiation. The system energy and exergy analysis were carried out separately for the solar field, power block, and overall solar power plant. The solar field efficiency was calculated by the relation between the energy or exergy content in the terminal and the all energy or exergy that enter in the collectors. The power block efficiency can be determined through the relation among the net power generated by the system and the energy or exergy content in the terminal. The efficiency of the overall system can be calculated dividing the net power generated in the system by the all energy or exergy rates received by the concentrator. Since the local TNI considerably impacts the solar power plant's performance, this variable was also investigated. From all TNI values available at the database, it was chosen the day with the highest average daily radiation. The daily TNI used in the simulation is exposed in the graphic below. In this specific analysis, the solar field area required by the solar field was kept fixed, so that it was possible to account the net power generated for the system under the solar radiation variation. In order to ensure data reliability, the heat transfer model of the solar field was validated, so it was possible to verify that the proposed model presented a similar trend when compared to experimental data from the study of Dudler et al. Besides, the power block was validated with the study of Hayegan et al. With a reliability greater than 97%. Here we can see the thermodynamic properties, temperatures and pressure, and the mass flow rates of all strings of the proposed system, and a schematic of its TS diagram. The pressure drops in the pipes and heat exchangers were neglected, and the organic fluid is fed the turbine as saturated vapor and leave the condenser as saturated liquid. From these results, it was possible to infer that the mass flow rate required by the terminal in the solar field was almost twice as high that one demanded by the organic fluid in the power block. The pressure drop in the solar field was 37.6 kilopascal, and it was necessary a receiver tube with a total length of 356.2 meters and an aperture area of 2,011 square meters. In order to better understand the energetic flow by the system, we have a Sankey diagram showing the main energy losses in each system component. The overall solar energy rate focused by the collector was 1,442 kilowatts. Due to the heat losses related to the optical parameters that can be caused by imperfection in the collector mirrors, track errors, shading, and cleanness, only a portion was observed by the receiver. Because of the temperature difference between the receiver and the environment, a quantity of 84.2 kilowatts from the heat absorbed by the receiver was lost to surrounding by convection and radiation. The useful heat rate delivered to the terminal was 936.7 kilowatts, promoting to the solar field an energetic efficiency of 64.97%. In the power block, all the heat content of the terminal was transferred to the organic fluid, since the heat exchanger thermal effectiveness assumed was 100%. However, most of the heat rate that enters into the power block is rejected to the water in the condenser. Since the net power generated by the system is 200 kilowatt, it caused a power block energetic efficiency of 21.36%. As a result, the overall energetic efficiency of the system was 13.87%. Here we have a Grassmann diagram to demonstrate in detail the exergy losses and destructions in the system. As can be seen initially, the overall exergy rate available in the solar collector was 1,342.8 kilowatts, but an amount of 40.9% was destroyed due to the temperature difference between sun and the receiver, and 29.2% was lost because of the optical imperfection. In the receiver, the thermal exergy loss rate was the most relevant, 34.2 kilowatts. Because of these losses, the solar field exergetic efficiency was 27.37%. In the power block, the total exergy losses and destruction rates was 167.4 kilowatts. Considering this specific parameter, this exergy destruction in the evaporator and the condenser was the most relevant, since less than half of the useful exergy rate available to the power block was lost or destroyed, so that the exergetic efficiency of the power block reached 54.45%, and the overall exergetic efficiency of the system was 14.89%. To clarify the exergetic analysis, we have a graph that compares the magnitude of all rates of exergy losses and destroyed in the entire system. The solar field was responsible for approximately 85% of all exergy lost and destroyed. The most portion of the exergy destruction rate was due to the temperature difference between the sun and the receiver, and the most part of the exergy losses happened as a result of the optical imperfections. On the other hand, the power block just accounted for about 15% of all exergy lost and destroyed in the system. The major reason for this result may be associated to the lower operating temperatures in the power block when compared to the solar field. This graphic shows the power net generated by the system and mass flow rates of the terminal and cyclohexane under a DNI variation. As can be verified, the higher DNI value, the better the system performance. From 7 a.m. until 4 p.m., the system was able to exceed the design power. The maximum generated power happened at 11 a.m. From 5 to 7 a.m. and from 5 to 6 p.m., the power generated by the systems is lower than the design power. The overall power generated was 2,907 kilowatt-hours per day. Following the trend of the net power, the mass flow rates of the terminal and cyclohexane also enhanced with the DNI increasing. The peak of the mass flow rate was also at 11 a.m. In this table, we will have a comparison between the efficiencies achieved for the maximal and the minimal DNI. With the exception of the efficiency of the power block, which remained constant, all other efficiency enhanced with the increase in the DNI, since the higher DNI, the greater the energy and exergy available to the system. Considering the power block efficiencies, they kept the same value because of the variation on the mass flow rates of the terminal and the cyclohexane were the same. The main conclusion of this work is that the area required by the solar field was 2,011 square meters, and the pressure drop in the receiver tube was 37.6 kilopascal. In the solar field, The most energy loss was due to the imperfections in the optical system. However, the heat rejected in the condenser was the greatest source of energy loss in the system. Regarding to the exergy analysis, the solar field was responsible for the most exergy losses and destruction in the system. Moreover, it is important to state that the exergetic destruction from the sun to the receiver is the most significant. In the power block, the exergy destruction rate in the evaporator and condenser was approximately twice the rate of exergy destroyed in the turbine and that was lost in the condenser. The DNI variation showed that the higher the NE value, the better the system performance. Also, the mass flow rate of the terminal and the cyclohexane also enhanced with the DNI increasing. The overall power generated in the day chosen for this analysis was 2,907 kilowatt-hour per day. Here you have the reference of this study. Thank you very much.